Hi everyone. So in today's video, we're going to be talking about that term called the mole and how it relates to a very similar sounding word called a molecule. And we're going to be utilizing a value, a constant value that's called Avogadro's number to relate the two. So first, I always like to talk about the fact that the term a mole always refers to one specific number. So it kind of acts like a counter. So these five words on the screen are words that are always associated with one specific number. So when we talk about a pair of something, we're referring to two of that item. A dozen is 12. A ream of paper is 500 sheets of paper. Fortnite is more than just a video game. A fortnight is actually, thanks to William Shakespeare, 2 weeks of time. And then if you've ever told anybody to just wait a moment, officially a moment is exactly 90 seconds in length. So if you tell somebody to just hang on a moment, they have to wait a minute and a half. All right, one more counter that I like to talk about is a term called a smoot. And Oliver Smoot was a fraternity member at MIT. And as a pledge task to join this fraternity, he and all of his buddies, this is Smoot here laying down on the ground, measured the length of the Harvard Bridge in how many body lengths it was. So they used his body as a way to measure the length of the bridge. And his friends not only marked head to toe where he was, but then they picked him up by the wrists and by the ankles and then laid him down and then marked again and then laid him down over and over again. And this guy, Oliver Smoot, was just so obsessed with measurement and precision that he started to work for the Departments of Standards and Measurement for the United States government. And if you Google how tall Oliver Smoot was, you can actually convert a certain length into smoots. So one smoot is exactly 5.58333 feet, or specifically how tall he was. He's 5'7". And then if you're wondering how long the Harvard Bridge was, it spans across the river just outside MIT and Harvard. And that bridge every year is measured by the same fraternity as an homage to Oliver Smoot. And it's 364.4 smoots long. So they picked him up and set him down 364.4 times. All right, but again, all I'm trying to drive is that this term smoot refers to one number every single time, the same as a dozen always refers to 12. So when chemistry, when we talk about a mole is this ridiculously large number of anything. Just like a dozen balloons is 12 balloons, and a dozen bowling balls is 12 bowling balls. So a mole of bowling balls is this many bowling balls. All right. But specifically in chemistry, we use that to represent the number of atoms or molecules within a substance. All right. Now we have a much simpler way of writing this number, which saves us a lot of time. It's called scientific notation. And so the equation that we use is that 1 mole of anything is equal to 6.02 times 10 to the 23rd power. And then the unit for this number could be atoms, molecules, or even something generic like particles. But because these two values are equal to each other, we can use them set up as a fraction. Remember that thing we did a while back called dimensional analysis is going to be utilized a lot more as we go throughout the rest of the school year. All right, so I want to take a little bit of time just to talk about some of the common terms that we're going to see because some of their abbreviations are really similar to one another. All right, so the first one is a mole, and it's a unit for a large collection of atoms or molecules. And the abbreviation for mole isn't much of an abbreviation, but we just simply write MOL. We cut the E off. Saves us 1 second of our life, right? When we talk about individual components of a mole, that's when we use terms like molecule, particles, and atoms, right? And the abbreviation for molecule to differentiate it from mole is MOLEC, right? And a molecule is individual components of a mole, but several atoms bonded together. So, like water molecules are hydrogen atoms and oxygen atoms bonded together. All right. Particles are just kind of a generic term. It's like when you refer to a bee as an insect or a beetle as a bug. There's a lot more specific things that could be used to identify, better terms to identify those particular animals. But for particles or something like that, sometimes we just refer to them as particles as like one generic term. All right, so the abbreviation for particles is just part. And then when we talk about atoms, atoms can again be individual components of a mole, but these are singular components of an element. So lithium atoms or carbon atoms or lead atoms. All right, the last one that we'll use is something called a formula unit, and that refers to individual ionic compounds. So an ionic compound doesn't really get referred to as a molecule because molecules are more of the molecular compounds, the nonmetals bonded to nonmetals, and then formula units are what we use when we talk about metals bonded to nonmetals. And if you've been paying attention to how some of these abbreviations work, yes, you guessed it, that the abbreviation for a formula unit is an FU. So this is one of the very rare few times in all of education that you get to write FU to a teacher on a test or a quiz. So let's do some practice problems. If we're asked to convert 4.8 moles of water into molecules of water, we would start by writing out the number, the abbreviation for mole, MOL, and then the formula H2O. And remember, with dimensional analysis, these units we want to place in that first denominator so that when we multiply by this fraction, those will ultimately cancel out. All right, and the one equation that we know is true is that 1 mole of anything is equal to 6.02 times 10 to the 23rd. So we can put 6.02 times 10 to the 23rd individual molecules in the numerator, and we would simply multiply these two numbers, divide by 1, and we would get the final answer of 2.9 times 10 to the 24th molecules. All right, now this is something that I will say in class, and that is that we need to really practice using our calculator. We're going to be working with numbers that are in this really, really large scale, and sometimes you might have the work written out correctly, but it might just be keyed into your calculator incorrectly. Sometimes you just need to get a handle on how exactly do I type these numbers in, and how do I get the correct answer using the correct buttons on the calculator. Okay, so if we were to go the opposite direction, if we're told that we have 7.6 times 10 to the 21st atoms of boron, and we're asked to figure out how many total moles of boron is that. All right, we again start by writing our number, 7.6 times 10 to the 21st atoms, and then the symbol for the atom, boron, B. And then we're going to put atoms in the denominator, and this time we put Avogadro's number, 6.02 times 10 to the 23rd, in the denominator, and that's equal to 1 mole of those large number of atoms. So by having the units in the correct location, we now see that we have to take this number and divide it by 6.02 times 10 to the 23rd, and that gets us the final answer is 0.013. This is the one where if you mistype it in your calculator, you get some really weird answers. All right, but I also like to point out that this number, 6.02 times 10 to the 23rd, is standardized. 1 mole equals this number every single time. So if our starting number is less than that, times 10 to the 21st, this is a smaller number than times 10 to the 23rd. Because this is less than what 1 mole equals, we don't have an entire mole of boron. We have less than a mole. So our answer should be a decimal value. If this was 7.6 times 10 to the 28th moles, where we have more than this value, then our number should be greater than 1. So there's a little bit of logic that could be utilized to determine whether or not our final answer is in the right spot. All right, one last example problem. We're now asked to find how many atoms of oxygen are in 2 moles of iron 3 oxide. So one component to this is getting the correct formula for iron 3 oxide, which is Fe2O3, right? And so if we were to go from moles to individual compounds, formula units, we would do for every 1 mole, there's 6.02 times 10 to the 23rd, so we would just multiply that by 2. But within each formula unit, there are 3 individual atoms of oxygen. So we can use the actual chemical formula as a second ratio. Same practice as before, we would start with our number value, 2.0 moles of iron 3 oxide, 2.0 moles Fe2O3, and put that in the denominator. And then we know that that's equivalent to 6.02 times 10 to the 23rd formula units. And then our second conversion factor states that for every 1 formula unit, or for each Fe2O3 compound, there will be 3 atoms of oxygen. So 2 times Avogadro's number, 6.02 times 10 to the 23rd, times 3 is equal to, in total, 3.6 times 10 to the 24th atoms of oxygen.